Hi guys. So hope you spend some time on this. Now this is slightly involved derivation, so just let's go through it step by step and very carefully. Right? So now, as I said, the principle I'm going to use is, or the concept I'm going to use is electric field E vector. Right? This is equal to minus, right, del V by del X into I cap plus del V by del Y into J cap plus del V by del Z into K cap. Right? Which basically what I'm saying is at any point take three perpendicular axes X, Y and Z, right? And then find the gradient. What is the gradient? Gradient is if I make let's say if we had X, Y and Z, so if I go a small distance, if I move a small distance along X axis, right, how much is the change in potential? And the ratio of the change in potential and the distance, right, that would give you the gradient in the X axis, along the X axis, and the negative of that would be the electric field along the X axis, and so on. Okay, so now let's work this out. So now I want to find the electric field, right? So we need to find the electric field. Right? This is my goal, right? And if I have to find the electric field, I need to find the components, right? So I need to choose what are my axes. So here what I'm going to do is, for convenience, right, I will take one axis which should be along the radius, right? So this would be along this position vector r, and let this be this axis, and I'll take one which is perpendicular to this, right? I'll take one axis which is perpendicular to this, right? So now now forget about all this, just think about, what will the electric field direction look like? So electric field because of this would be along this line, would be somewhere, this is negative, so it would be actually towards R, right? Why towards R? Because electric field is nothing but force on 1 unit charge. So if I have 1 unit charge here, this minus Q would pull it towards itself, right? So you would have one pull would be along this direction. So there would be one pull, right, along this direction, and this guy would push it along this direction, right? So this plus Q would have some electric field along this direction, and the resultant would be the vector sum of those two. And I'm going to resolve that along these two axes. So this is one of my axes, this is my second axis, and here this axis I would say this is a unit vector along this one. I'm going to call it R cap. Why R cap? Just a convenient name. So R is my position vector. So unit vector along R, I'm going to call it R cap. So the vector of magnitude 1 along this line, this is my R cap, and perpendicular to that, right, I'm going to define another unit vector which I'm going to call theta cap. Right? By the way, the theta cap is not an angle, it's a unit vector, it's a name, theta cap. I could have called it anything else, right? So this theta cap, what is it? It is a vector of magnitude 1, right, but along this line perpendicular to the position vector line. Okay, now we know that since the pull and push is going to be in this plane, right, the resultant also will be in this plane, so there will be no component of electric field perpendicular to this axis. It will be only, the components will be only along these two axes. So now I have a two-dimensional problem. Okay, I have only a two-dimensional problem, and the result would be the electric field would be in this plane. So now let me try to find out, how I can get the R component and the theta component, so to say. R is along the position vector, theta is perpendicular, right? So I'm going to call it R component and theta component. Okay. Now here we said that, okay, so if I want to take any axis, let's say I take X axis, so then my E is minus dV by dx, right? So now I'll use the same logic here. So let us say if I cause a small displacement, so this is my R, this length is R, I take a small displacement here, right, and I call it, let us say, dr. Okay, call it dr. So if I find the delta V here, or dV, right, if I find the corresponding to this dr, if I find dV, then my electric field component along that axis, along this axis would be, I'll call it my E radial or ER, right? But by the way, why do this word radial? Because if you think of this as center, this is like the radius, right? So I'm going to call it the ER, right? E radial right, which is along this direction. So my E radial would be minus del V by del R, right. Think of R as my x-axis here, right. So this is, if it was x-axis, I would say del V by del X into I cap. So it is del V, so ER would be minus del V by del R into R cap. That's it. It's nothing different. It's the exact same thing, right. So now let's find out del V by del R. So now what is, so now how much will V change? Now we know the equation for, so this is the formula for V, right. Now I can find del V by del R from this, right. By the way, just to recap, when we say del, what does it mean? It means differentiate V with respect to R while keeping other variables constant. Treat the other variables as constant. So we are moving along this line. So which means, which are the variables here? R and theta. So everything else is constant, right? So here I am moving along this line. So my theta is not changing. Theta is constant. Okay, that's what it means. Okay, so now my del V by del R would be del by del R of P cos theta upon 4 pi epsilon naught, right, into R square, right? And here P and 4 pi epsilon naught there, and even cos theta, we are treating it as constant. So all these are constant, so we'll take them out as a coefficient. So this will be P cos theta upon 4 pi epsilon naught, right, and this would be del by del R, right, of 1 upon R square, right? And this will be nothing but simple derivative of 1 upon R square, which is what? So this is R to the power minus 2, so this would be minus 2 upon R cube, right? So now we'll say del V by del R, right, is equal to, so this will be minus 2 upon R cube, so I'll bring minus 2 here, so it will be minus 2 P cos theta, right, upon 4 pi epsilon naught, and this would be R cube. Right. So this is going to be my del V by del R, right. So this is so here I have found the component along the position vector or the radial component. So this is my first thing that I wanted to find out, okay. This and the electric field, by the way, would be negative of this, right. So this is the gradient along this, and E is going to be minus of this thing, right, minus 2 P cos theta upon this thing. Now let's look at how will I find the perpendicular component. It involves a little more thinking, so let me help you with that. Right? So let us say I go from here, I cover a small distance, right, and let's say I call this point, let me call this A, and let me call this point B, right. Now here what would be so this is, we did equivalent of what was del V by del X. Now I'm taking the perpendicular direction, right. So again, so it will be, so what will be the component here? So here I would say my E theta, right, E theta, right, this would be minus del V, change in V, right, divided by change in distance, right. What is the distance here? Distance is AB, right, del V by AB, right, this into theta cap. Theta cap, think of theta cap as my J cap, okay. This is just, since it's perpendicular, and we give it a name theta cap, but that's just a name, okay. So now what is my AB? If you look at AB, how do we find this AB, right? I know theta, right? So if I were to connect this, right? If I connect this, if this is my theta, right? This is going to be my small change in theta, and I'm going to call this d theta, right? And this distance is r, right? And by the way, because this is very large, right? So this side, I call this O. So OA and OB, they would be approximately equal, okay? So now this is like, so if this is d theta, what will this length AB be? So this is r. So this is so angle d theta is nothing but d theta is going to be, d theta is equal to arc upon radius. So AB is approximately like the arc, so this would be AB upon radius r, and therefore AB is equal to r d theta. AB is equal to r d theta. Right? So, and why are we doing this? Because we know that I know V is a function of theta and r, so you want everything else in terms of theta and r. Then it will make our job easier, right? So now I can write this as, E theta, right? E theta, this is equal to minus del V by, and this AB, so it's going to minus r d theta, right? And here when I move in this direction, I am keeping my r constant. Remember, here this is only r is changing, here only theta is changing, right? Here r is constant, therefore I can write this as r del theta, because my r is constant. I am keeping my r constant. So when the differentiation is done such that one variable is kept constant, we use the symbol del, right? Into theta cap. Right? Don't forget this r. It's very, very important, right? Rest of it actually will not be. Now it's simple. This is the only thing, which is a little tricky. So I wanted you to understand this properly. Now let's just find del V by r del V by del theta. So what will that be? So del V by del theta, right, would be, just differentiate this with respect to theta, keeping r constant. So this would be del by del theta, right, of P cos theta upon 4 pi epsilon naught r square. So now here P and the denominator, everything is to be treated as constant, right? So it will come out as coefficient. So we'd have P upon 4 pi epsilon naught r square into, and now we are doing just del by del theta of cos theta, right? And what is del by del theta of cos theta? It's nothing but differential of cos theta is minus sin theta. So this would be minus P sin theta upon 4 pi epsilon naught r square, right? This is my del V by del theta, and now my E, total electric field, what will this be? This would be minus of del V by del of one variable into the unit vector along that variable, plus del V by del of other variable into unit vector along that variable, right? So and negative outside, right? So my E vector is now going to be, right, minus del V by del r, right, into r cap, plus del V by r del theta. Don't forget this r, huh? Del V by r del theta into theta cap, and rest is fairly straightforward. So take these two values. So first variable del V by del r, where is that? That is here, and second variable del V by del theta is this one. So now I can write this as, and both have minus, so I'll cancel the minus here. So we'll find the electric field is equal to, right? So the minus sign gets cancelled, rest of it will be the same. So it will be 2p cos theta, right, upon 4 pi epsilon naught r cube, right, and this into r cap, plus, again this minus and minus will cancel, plus p sin theta upon 4 pi epsilon naught, this is r square, but remember there is an extra r here, right? So this would be again r cube into theta in vector. So this is going to be my total electric field vector, right? The two components, and there's no perpendicular component that we already discussed, right? So now just let's look at this, right? So what does this tell us? So what I'll do is I'll ask you to think about this, right? This is the overall field, but if I were to take, so there are two interesting questions. One is, what if an object is along the axis of dipole? A special case. There are two special cases I'd like to talk about. One is, what if an object is along the axis? What will be the electric field here? From there we can find out. And second, if I take an object here, right, which is along the perpendicular axis, right, as a special case, what will be the electric field there? Right? Now, it's not very hard to figure it out, but I will give it to you as an exercise. Right? And if you want, we can discuss this in one of the future videos. Right? So just work this out, and we'll discuss the solution next time. Thank you.